Nobody's over here. Like, they'll be running full speed, right? And then they do one of the stupid drop off. This is the call. He's the ball.
Bro, I texted you about this.
It's like dump the ball. You dump the It's like or if your final grade is like your final score is better than that, that's it. I never see so actually do on basketball.
She said you got 4 days ago.
I feel he's probably like I feel like some of the defensive stuff.
Oh, I totally forgot about that. It's probably not happening.
Yeah, I'm sure it's your boss. You guys think get out of here, Rob. There was other people that chance.
I mean, I think I think I just read, because like, for the previous video, I thought it was genius, but like, it was like, a little low. This one I thought it was like, it wasn't easy. It was really good. And she's like, she's even fine.
Alright, I'm gonna get started. So I'm gonna do this a little differently to make the actual review session part here a little more interactive than me just standing up here and writing on my laptop. I actually have pre-done notes which are online that I'm gonna scroll through on my laptop. So if you're on your screen, you'll see what I'm looking at. And hopefully this kind of recording will make it a little more interactive for the people here. At least for the first part. The second part is ODEs, which I guess for that, I'll just sit down and I'll just start writing on my computer. But at least for this first part, hopefully I'll put stuff up on the board and then we'll take a break about halfway through because I can't talk for 3 hours at a time. And then we'll go to the ODE section. All right, so before we get started, does anyone have any questions regarding the logistics of the exam? So I'll answer all of those at the beginning. Yeah.
Where's it located?
Yeah, I think it's in Huntsman, G06, that big auditorium in Huntsman. So if you go in the Walnut entrance of Huntsman, that's the closest way.
Okay.
It's literally right there as you enter. Sorry? The notes, they should just be in the OneDrive notebook. If you follow the stream online, you'll see them online. Yeah. But if you just follow like the Twitch stream, you can see them as we go along. Any other questions? All right, so let's get started. What are we going to cover today? So what I have, I'm not going to talk about anything before chapter 4. So I think what a lot of the stuff before chapter 4 is just that you need to know the definitions. So there is a definition sheet online, which is essentially finished for all linear algebra, and I think that's like more of what you should be worrying about with definitions. I mean, when we get to like diffie-qs, there's really not that many definitions involved with diffie-qs, so there's really no point in me like trying to hammer out that diffie-q definition sheet. So anything before chapter 4, you should definitely look at the definition sheet. Some of the more important stuff, you should probably know like the like different properties, like transpose inverse properties. There's like the invertible matrix theorem. What else? You got like your determinant properties. And then you have this pretty important thing where you have like the relationship between rank and consistency of a system, right? So consistency of homogeneous or non-homogeneous systems. So that's pretty much everything before chapter 4. I think if you're gonna get tested on anything, like you just really need to know the definitions. Like you might need to know like AB transpose. Like you might need to use like AB transpose. I think a lot of these will also be on like the true/false. There tend to be fair game there. You might get like an easy question at the beginning. That's like, I think in our midterm 1, we had like this big ass matrix, and then it was just like find something that like either solve the system or find some unknown values. So those are like kind of the types of problems I would expect from the earlier sections before chapter 4. But really, the real material starts after chapter 4. So let's talk about 4.2. Vector spaces, and 4.3, which are subspaces. Okay. So when we talk about vector spaces and subspaces, we're usually going to talk about, remember that subspaces are like smaller dimensional vector spaces inside a bigger one. Right, so that's how we always, so for the purposes of this class, whenever we give you something and we ask if it's a vector space, generally speaking, if you can identify like the larger vector space, then you just have to say, okay, I just need to show closure under addition and then closure under scalar multiplication, right? So a subspace S is a subspace of V if closed under addition and closed under scalar multiplication. Okay, and let's go through some problems then of dealing with subspaces and asking ourselves, are these subspaces? So is the following a subspace? Okay, so is the following a subspace? And we'll start off with one, continuous functions on an interval AB such that f of -1 times f of 1 is equal to 0. Okay, so when you ever have, if you're not already given in like subset form, it's really easy, or not easy, but it makes the problem a lot easier if you're able to put this into some kind of set notation, right? And so whenever you have like a such that, this is going to be your condition. So our set then is going to be s, and then we're going to have some kind of continuous function on an interval. So I'm going to call this continuous function, well, we have them called f over here, so I'm going to call it f of x on an interval AB, or f of x inside, f of x are continuous functions C of AB, that's what continuous functions on an interval is. So this is like the bigger vector space, such that f of -1 times f of 1 is equal to 0. So this is our set notation, right? And so this is like element, this is a general element in the set, f of x. And then this is the condition that that general element has to satisfy. Okay? And so we can claim that this is, so if we didn't know that this was a subspace, we can claim that it's a subspace by saying that all continuous functions are are a vector space. All right, that's just like a given. Yeah, so if you see like all functions, all continuous functions, all solutions to diffy Qs, just say that that's like a vector space. All right, so let's show closure under addition if we can. And so what do I want to do? I want to take two general elements and like smush them together, right? So I want to see if f plus g, right, of -1 times f plus g of 1 is equal to 0. Right, so I took two elements so I took f and g inside AB, so I probably should have written that first. So take f and g inside the continuous functions of AB, or you can think of it as inside S, right? So take f and g inside S, and then we add them together, right? And we want to see if it satisfies the condition. And so what happens here is that you can actually like distribute this like plus term here. So this is really like f of -1 plus g of -1, like as a quantity. I'm going to raise that a little bit. Knock that down. And then over here, this is like f of 1 plus g of 1, right, as a quantity. And so if you FOIL this out, you get f of -1, f of 1, plus f of -1, g of 1, plus g of -1, f of 1, plus g of -1, g of 1. Right? But this guy is 0, f of -1, f of 1. G of -1, g of 1 is 0. But the problem is, I can't say that about the middle two terms. Right? So these middle two terms might not be 0. So we can write like equals 0 and then with a question mark there. Right? We don't know if they're 0 or not. So in conclusion, this isn't closed. Under addition. So it's not a vector, not a subspace, at least. All right? And so the important thing about dealing with these kinds of problems is that I think a lot of students like have trouble wrapping their head around like what gets added. So a really common mistake is like they take f of x plus y, right? But you're not taking a general element in that point, right? Because our general element is the function f, not the x inside, not the point inside the function. Does that make sense? So you don't want to end up Like if you wrote of f of x plus y is equal to f of x plus f of y, like if you're trying to check this, it's not the right thing. You're not checking the right thing. All right? No, not that. Don't check that. Okay. So that's first problem. All right. Next problem is then, so number 2, let's take S. So is x1, x2, x3 inside R3. All right? And then such that x1 is equal to 2x3. Okay, so is this a subspace of R3? Okay, so what is our general element? Our general element is x1, x2, x3, and then the condition that it has to satisfy is x1 is equal to 2x3. All right, so now what? So if I'm checking closure under addition, I want to take two general elements, and so I'll take x1, x2, x3, and let's say y1, y2, y3 inside S. All right, take two general elements inside my subspace. And then what do I want? I want to add them together, right? So I want to see if x1 plus y1, comma, x2 plus y2, comma, x3 plus y3 is this in S. Okay, and the idea then here is, all right, what is x1 plus y1? Well, we know x1 is 2x3, and that means y1 has to be 2y3, right? And so here, this is really like 2x3 plus 2y3, x2 plus y2, x3 plus y3. All right, and then we can factor out a 2 here, so that's 2x3 plus y3, x2 plus y2, x3 plus y3, right? And so we have that this first term is essentially 2 times some x, like some, you could call this like z3, or like, yeah, so you can say like this is like z3, or something like that. You can call this like z3, and then you can call this z3, and then this first entry is like z1 is equal to 2z3. Right? Essentially, the first term is 2 times the third term, which is what we want inside our set. So this holds under addition. All right, and then we want scalar multiplication. So now we take some constant in R, and then x1, x2, x3 inside my set, right? And then now is k times x1 plus y, k x1, x2, x3 inside the set. And then we do the same thing. We multiply k in. You get kx1, kx2, kx3. And then you know that x1 is equal to 2x3 from the condition. So that's 2kx3, kx2, kx3. And then again, right, the first term in the vector is just 2 times the third term. And so this is in the subspace, and we're good. Okay. So this is closed under addition. This is a subset. Okay. Any questions? Or subspace, not subset. All right, and then let's go over here. Okay, and so now number 3 is the following. We'll just say S is solutions to the diffie q, t squared y double prime minus ty, ty prime minus y is equal to ln t. Right, so what is a solution? This is really like y is a function of t that satisfies the diffie q. So this should be like y is an element of continuous functions in continuous functions greater than 0, right? So, 0 to infinity. Okay. Oh, that's an awkward curly brace cutoff. There we go. Okay, so we want to find all y's such that this diffie q is satisfied. And so here, before even checking the two, I'm just going to note that 0 is not a solution, right? 0 is not in S. That's because 0 doesn't satisfy this diffie q. If you plug in 0, right, you get 0, not ln t. So 0 is not in S, so therefore not a subspace. So that's the easiest check, right? If 0 is not in your subspace, then, or if 0 is not in your subset, it's not going to be a subspace. Okay, any questions? Yeah?
So on your stream it says T ln T, but does that say T?
It doesn't matter. The right-hand side's not 0. Like, yeah, if the right-hand side were 0, then it would actually be a subspace. But in this case, the point is the right-hand side's not 0. Any other questions? Yeah.
If like there is a soft bracket around the 0 instead of hard bracket there for y first.
Oh yeah, it should be a soft bracket, right? Yeah.
Oh, it's still not true. Oh, okay.
So you don't want 0 because you don't want ln 0. But yeah, but this just, I guess the moral of the story is anytime you have a non-homogeneous diffie q, any solutions to a non-homogeneous diffie q is not going to be like a subspace. Yeah. And that also holds like not just for diffie q's, but like systems of equations as well. Right? If this were like matrices, vectors x such that ax is equal to b, where b is not 0, then that's also not a subspace. Okay. Any questions? Okay, so any questions on subspaces before I move on? Okay, so let's talk about so 1443 subspaces. 4,4 is span. Okay. So again, 4,4 span. So I'm not gonna do an example of span because I have one later on that we talk about span because it's really important in bases. But in general, right, the span of a set of vectors are all. So if you have a set of vectors v1, v2, vn, then the span is just all linear combinations of v1 through vn. So those are like c1, v1 plus c2, v2, etc. So that's the span. Let's see, what do I have written here? I actually don't have anything written here, right? Yeah. That's all for a span. Yeah.
Vectors of span, they have to be linear independent.
The vector? No. Well, so you're thinking ahead to like bases, where like if it's a basis, then you have to have linear independence. But just in general, like you can have like in a set of vectors, right? So this is just any arbitrary set. It doesn't matter. Okay. Okay. So talk about linear independence then. So I think throughout this class, we've learned a lot of different types of linear independence type of. So we've learned a lot of different ways of calculating linear independence, and so we need to know the difference between the linear independence of just vectors, functions, and then vector functions. Right? So there are essentially three different types of things. So where do we see these? Vectors, they're just literally just like, you can think of them as like columns of a matrix. Right? So just columns of a like matrix with like constant coefficients. And then functions, we usually check linear independence of functions when we care about like solutions to diffie Qs, right? And then for vector functions, we usually care about linear independence when we check solutions to what? Systems of diffie Qs, yeah. All right. So the one way that's always going to work then, when we talk about linear independence, is the following, right? For vectors, or for all three of these, and well, not functions. So for vectors and vector functions, right? The definition is V1, V2 through Vn are linearly independent if and only if C1 V1 plus C2 V2 plus Cn Vn equals 0. Equals the 0 vector has only one solution, which is C1 equals C2 equals Cn equals the 0 vector. Right, so this is like the default definition that is like a fallback if nothing else seems to work. So, for example, so let's see, this goes up, that comes down. Yeah.
Shouldn't that be 0 instead of the 0 vector? Because like when you multiply the 0
No,
because you have like when you
this is
multiply,
a constant times a vector though.
so it's like shouldn't C1 and C2 be 0 and not the 0 vector?
Oh, I see. Yeah. These constants are 0. Right. Yeah, I thought you were talking about here. You're good. Yep. Okay, so let's take a look at an example then. Right? Show that the following, find k such that and then you got these vectors 0, 1, k, 0, 1, 0, negative k, 1, 0, k2, and 1, k, 0, k are linearly independent. Okay? All right. So here's the thing. if this were a square, if we like threw all these together and we got a square matrix, we could find it immediately by like taking the determinant and making sure that the determinant wasn't 0, right? But in this case, it's not a square matrix, so we can fall back to the trusty definition over here. And so now we have, right, C1 times that first vector plus C2 times the second vector plus C3 times the third vector is equal to the 0 vector. And so now we can throw this into a matrix system where we have 0, 1, 0, negative k, 1, 0, k2, and 1, k, 0, k, augmented with 0, 0, 0, 0. And essentially, how do I find if this system gets me linearly independent or linearly dependent vectors? Yeah.
The system's inconsistent.
Yeah. Oh, well, it's always going to be consistent.
Always consistent for.
Well, the right-hand side's 0, so it's never going to be inconsistent. Yeah, so it's not an inconsistent issue. Right? How many solutions are we looking for? 1. Right? So what rank does this matrix need to be?
3.
Yeah, it needs to be full column rank, or it needs to be rank 3. Right? Otherwise, I'll have a free variable, and then I'll have infinite numbers of solutions, which is not what I want. So here, I want this to be rank 3. All right, so let's just row reduce then and see what happens. So this will be 1, 0, k, 0. I'll switch row 1 and row 2. And this will be 0. Oh, did I changed this, I think. So here, this should be a k. So 1 k, k. Oh, that's unfortunate. But yeah. All right. So there we go. Make that change there. It's in the notes, I think, except for the beginning. But swap that 0 out for a k in the third vector. And then, so now what do I get? 1, 0, k, 0, 1, 1, 0, k, k, negative k, 2, k. Okay, so what happens, these two rows just kill each other. So I'll move one of them down to the bottom. So I got 1, 0, k, 0, 0, 1, 1, 0, and then 0, 0, 0, 0 on the bottom. And so now I got to deal with this negative k here. So I multiply the first row by k, and then I'll add it to the fourth row. And then so now they'll get 0, 2 plus 0 is 2, and then 2 k plus k squared. Okay, and then finally I got to 0 out this 2, and so what do? I do minus 2 times row 2. So I get 1, 0, k, 0, 1, 1, 0, 0, k squared plus k minus 2, and then a row of zeros at the bottom, and then a bunch of zeros on the right-hand side. Okay, so why does this system have infinite solutions? Yeah, when this guy in the third column, right? Third column, third row is 0. Right, so we have, so it's linearly independent if k squared plus k minus 2 is not equal to 0. Right, so we want this term to be not 0. And then what happens, well, just factor and solve for k, and you'll get k is equal to negative 2 and positive 1. Or not equal to negative 2 and positive 1. Right, so if k, so if k is not equal to negative 2 positive 1, then it's full column rank. So linearly independent. Okay, so that's how we deal with vectors. You can also do it for vector functions. Let's see, what do I have next here? Okay. Okay, so for the second example, we're going to talk about vector functions. Right? And for that, we're going to turn to homework 11, number 9. And so here, right, this was like a problem that said x1 of t was equal to e to the at cosine btr minus sine bts. And then x2 was equal to e to the at sine btr plus cosine bts. All right, do we remember this question? All right. There are a few more details, I think. We found these vectors as solutions. These are solutions to x prime is equal to ax, where a was n by n. Okay? And lambda was equal to a plus or minus bi. And we know that r and s are linearly independent vectors. Okay, so that's like all the information we have from this problem. Okay, so let's talk about how is this problem different from the problem up here. Yeah, so my vector is dependent on t, right? The value of that vector is dependent on t. So you might want to argue that, well, the value of the vector up there is dependent on k, but k is a constant, right? It's not changing with time, whereas here all of your entries are changing with time. So this is like a vector valued function, right? Rather than just a plain old vector of constants. Okay, and so when we have vector value functions, when we have vector functions, we can deal with them a little differently. And this is where I think this problem was written incorrectly, or I think they didn't mean it in a certain way. Because what do we want to do with vector value functions to determine linear independence? We want to throw it in a Wronskian, right? So what we want to do, right, we want to throw into a Wronskian at a point. All right, so what's a good point to throw these guys into? 0, right? So let t equal 0. X, 1 at 0. Well, what is that? E to the at, that's 1. Right, because t is 0. So we got e to the 0, which is 1. Cosine bt is 1. Sine of bt is 0. So this first term just simplifies to r. Right? And then what is x2? Well, x2 at 0, right, simplifies to s. So if I throw it into a Wronskian, right, the Wronskian at 0 is going to be the determinant of r, right? R is going to be one of the columns of the Wronskian, and then S is going to be the column of the other vector, right? What's the problem with this, though? No, it's not 0, but there's another problem.
You're not ruling for every point on.
No, so that's actually fine. There's a different problem. Yeah, it's not square. It's not necessarily square, right? Because what are the dimensions of A?
N into N.
N by N. So in particular, what should the dimension of R and S be? N by 1, right? And so if you throw these guys into this matrix and you're throwing two n by 1 matrices, two n by 1 vectors together, right? You got an n by 2 matrix. And try and take a determinant of an n by 2 matrix. That's only well defined if n is 2, right? So A had to be a 2 by 2 matrix. Otherwise, this determinant makes absolutely no sense, right? Think about it. You have tall column vectors going in, and you're trying to take a determinant. Okay? So this only works. So this determinant is not 0, right? And why is this determinant not 0 in the first place? Yeah, because you know R and S are linearly independent. Okay? But the problem here is that this assumes n equals 2. Okay? And this is where I think that they wrote the problem wrong, because I think their point was for you to use the Wronskian, but then they said it was for an n by n matrix. Yeah?
But doesn't n by n have to be 2 since the x vector would be x1, x2?
So they only give you two. This is just two solutions to the diffie q, right? You could have like, yeah, you could have like more solutions, right? So they just, yeah, I don't want to read minds. I think they wanted n to be 2, but like they just didn't say that in the original problem. Yeah. So this only holds if n is 2, which is perfectly fine. This is like a perfectly good way to do this problem if you knew A was a 2 by 2 matrix. Okay. So what if n is not equal to 2? How can you do this if n is not 2? Yeah, you gotta use the definition, right? So C1 times x1 plus C2 times x2 is equal to 0. This one is, it's not the greatest. I think you get like, from here, yeah, I think what you can say, you can't say much, but from here you just have to argue that C1 and C2 have to be 0. And when you know that cosine and sine are like linearly independent functions, and you know that R and S are linearly independent vectors, it's really hard to make a linear combination that gets you 0. And in fact, the only one that can get you 0 is C1 and C2 being 0. So you can like just make some argument for that. I think in the notes I didn't even do it out, and from here, I don't think there's really a good way to argue this. It'd be a lot easier if like this were an S and this were an R, but it's not. So it is what it is. Okay. And then yeah, so you get C1 x1 plus C2 x2 equals 0, and then just argue that C1 equals C2 equals 0 is the only solution. These should be linearly independent. Yeah.
So only at one point the Wronskian of the vector function.
Yeah. So we'll get to that. Yeah. But for a vector function, if it's not 0 at one point, you're good. Okay. Any other questions for this? I think this was the homework problem had good intentions. It's just that I think there's a little slight oversight with n equals 2. Okay. Let's see, number 3. So I don't really have an example for the third one, but when do we also use so then linearly independence of functions. So that was vector functions. So the third type of linear independence we can do is actual functions, right? And so here you have to use the Wronskian. There's actually no other way to do this. So the way you do this is the following, right? If you have y1, y2, yn, right? Then you set up the Wronskian of y1, y2, through yn at a point x, and that's equal to y1 of x, y2 of x, yn of x, right? And then you just got to take derivatives until you get a square matrix, all right? And so this is going to be y1 prime of x, y1 double prime of x, and then you go all the way down until this is like y1 to the n minus first derivative of x, and then same thing over here, you'll get y2 to the yn to the n minus 1 derivative of x. So that's your Wronskian, right? Take that determinant, and then if it's not equal to 0, then it's linearly independent. Okay? So, some comments, right? The first things first is that this definition here always works. All right, so this definition for vectors and vector functions, this should work. I don't think you can use it for functions. It's a little more unclear. And then let's talk about the Wronskian then in general, because I had a lot of questions about this, so we'll just lay it to rest for good. All right, so this is a general flowchart of a Wronskian. You plug in a point. All right, actually the first thing is make sure it's square. All right, don't want to take a Wronskian, don't want to take a determinant of a non-square matrix. Then you plug in a point. Then you evaluate the determinant. If it's non-zero, it's linearly independent. If it's zero, ask yourself what you were finding. Like, ask yourself, what Wronskian am I taking? If it's, let me see what this is here. Yeah, okay. If it's a solution to a DiffEq or an ODE, what can we say? Yeah, it's dependent. All right. If it's a solution to a system or just random functions, what can we say? Nothing, right? Go back to step one, plug in a different point. Okay, so that's essentially the end-all be-all of the Wronskian. So non-zero is always your friend. Okay, that's what you're going for. Zero is a little more complicated. All right, span. Okay, let's talk about bases. Right, so basis 4.6, and it's the following: a set of vectors v1 through vn forms a basis for a vector space V if two things hold. One, v1 through vn span, and two, v1 through vn are linearly independent. Whenever you're asked to show a basis, you must show these two things. All right? Always and always and always. Okay? There is a shortcut though, right? If you know that the vector space V is n-dimensional, right? And you have n vectors, what can we do? Well, we only need to show one of them. All right? So if you have n vectors in n-dimensional space, you can pick one. All right? You can pick span, or you can pick linear independence. All right? Because one automatically implies the other. Span implies linear independence, and linear independence implies span. So you only need to show one. All right, so you only need to show one of these, and then you got to state like, oh, because we're in n-dimensional space and we have n vectors, we can automatically get the other one. All right, so we're always looking, when we ask you to find a basis, we're always looking for why it spans and why it's linearly independent, okay? And sometimes the justification for one of them is because it spans or it's linearly independent, but you still have to like say why. So for example, there's a recitation homework problem. Right, so recitation homework 14, I think, number 4C. Right, so this is a true-false, but essentially ended up being like you had to show that this is true. So I want to show that the columns of e to the at span the solution space. X prime is equal to ax, where a is n by n. Okay? So, what do we need to show? We need to show span and we need to show linear independence, right? And what's the easy way to do this? The easy way to do this is try to get n vectors and try to justify it's an n-dimensional space. Right? So how can we justify that the solution space is n-dimensional?
A is n by n.
A is n by n, right? A is n by n, so we're going to have n linearly independent solutions, right? I think this is a true-false problem that we've drilled into your head over and over and over, right? A can be defective, it still has n linearly independent solutions. The same thing. Okay? So now we need to figure out, right, how many vectors we have with the columns. Well, what are the columns of e to the at? Columns of e to the at are e to the at times like 1, 0, 0, 0. Right? So it's just e to the at times like 1, right? Because this extracts the first column of any matrix. All right, and then the next column is e to the at times 0, 1, 0, right, all the way to 0, since this will extract the second column of the matrix, and etc., all the way down to e to the at times 0, 0, right, 0, 1. So in other words, the columns are like e to the at times e1, where e1 is the standard basis of Rn, e to the at times e2, and all the way down to e to the at times en, right? Because this matrix is n by n, so this column vector has to be n by 1. All right, so how many vectors do we have here? We have n vectors. Right? Everyone good with that? Right? We have n vectors because I have n columns, since e to the at is n by n. All right? So there's n vectors here. Okay, so I've justified that I have an n-dimensional vector space. I've justified that they're n vectors. All right? So now I can either show span or I can show linear independence. Right? So I'm going to show linear independence. Okay? And what's a good way of showing linear independence with vector value functions? Wronskian, given that it is square, right? Is this square? Yeah, because I have n vectors and I know they're n by 1. Okay, so it's going to be square. So what do I do? Let's evaluate the Wronskian at what point?
0.
Yeah, usually 0, right? Well, Wronskian is 0. So what is that? Well, that's e to the a times 0, e1, e to the a times 0, e2, all the way down to e to the a times 0 en, right? Take the determinant of that. Right, what is this? Well, e to the a0 is the identity matrix times e1. All right, and that's just going to be e1. Right, but what is e1? E1 is like 1, 0, 0, 0, right? All right, what about the second entry? Well, it's e to the a0 times e2, so that's 0, 1, 0, 0. Okay, and then now we go all the way over. E to the a0 en, that's 0, 0, 0, 1. So what do we have? Yeah, the identity matrix, right? Which is 1. This is not 0, so it's linearly independent. Okay? And then because we did all of this work to prep this problem, we automatically have span. Because we know we have n vectors in n-dimensional space. Okay, so this was the proper way to do this problem. I think we were generous, and we graded this very laxly, I think. So this is like, on the exam, like you need to do each and every part to get full marks. Let's see, what's next? Okay, so that, all right. Next part is change of bases. All right. Okay. All right, so let's talk about bases, change of bases, which is 4-7. All right, so this is where like I'm going to start like mixing a bunch of stuff together, because change of bases, linear transformations, and like eigenvalues, eigenvectors, they're like all kind of like interrelated. So I'll just like give you a heads up if I'm jumping sections. But change of basis. Alright, so there's a very plug-and-chuggy way of doing change of basis, right? Where you put one basis on one side, you put a basis on the other side, you row reduce, and you get your change of basis matrix. That doesn't always work though. Okay, because there's like the one homework problem where it's like partial fraction integration, you can't do that. So in general, the way you want to think about change of basis is the following. P from B to C, right? Okay, so this is one notation. The other notation is PBC, right? And that's equal to, all right, so let C, right, or let B be the basis, like B1, B2 through Bn, and let C be the basis C1, C2 through Cn, right? And what happens is that this change of basis matrix is going to be B1 written in terms of basis C, B2 written in terms of the coordinate of C, and then all the way down to Bn written as a coordinate of C. Right, so you take each basis vector of B and you write it in terms of C, and that's how we get this change of basis matrix P from B to C. Okay, so this is one way to do it. And again, if B and C are vectorizable, so vectorizable just means if you can put them into a matrix, then, right, you can just put like your B basis on one side, your C, okay, so we want B to C, so we put B on the left, C on the right, okay, and then we reduce to the identity matrix on the left, And then we got our change of basis matrix PVC on the right-hand side. Right? So this is the plug-and-chuggy way, whereas this top part with the P from B to C, that's the less plug-and-chuggy way. Okay, so on the stream, here's the plug-and-chuggy way. Right? You put C on one side, B on the other, and you reduce it to the identity matrix on one side. Okay, so this might not always work. And so let's take an example of when the plug-and-chuggy way might not work as well. So this is from a spring 2015 midterm. And it's the following. Let B be an ordered basis. Okay, yeah, sure, why not? For R2, is that R2? Yeah, R2. And that's V1, V2. Okay? And let C be an ordered basis for R2. And this is going to be V2, V1. Okay? So find PVC. Yeah. Okay? So again, how do we write PVC? Right? PVC, you write it as, so you want to write it as the first basis vector written in terms of C. So here's the B basis. So we take the first vector, which is V1, and we want to write this in terms of C. Right? And then we take the second basis vector, which is B2 over there. Over here it's V2. And we write that in terms of C. Okay? So what is V1 as a coordinate of C? Yeah, so it's A times V1 plus, sorry. So the C coordinates are V2 and V1, right? So this is going to be A times V2 plus B times V1. All right, and we're going to see that A is 1 and B is, or A is 0 and B is 1. All right, so here you get like AB is equal to 0, 1. Right, and then V2 written in terms of coordinate C, right? So that's also equal to AV2 plus BV1. But now A is 1 and B is 0. Right? So this is the ordered basis of C. This is the C basis, C1 and C2. And this is C1 and C2. Right? Or V1, yeah. So V2 is C1 and V1 is C2. Okay? And so now what do? You plug them back into this matrix. V1 as a coordinate of C is 0, 1. And then V2 as a coordinate of C is 1, 0. And there's your change of basis matrix, right? So if you actually came up with bases and did this problem using numbers, I don't think you get full points because you chose an explicit basis where you're supposed to show it for all bases of R2. Does that make sense? So that's why sometimes you can't do this. Okay. Okay, so a follow-up question to this problem is the following, and I don't think I have this in the notes. Yeah. I think if you had the top, you would just be fine. Yeah. I mean, it always doesn't hurt to show more work, right? Especially if you know it's correct work. So, up to you. Yeah. Wait. Okay. Let's see. Am I supposed to move to that board now? Yeah, I think so. Okay. No, I'm not. Yeah. Okay.
I think you're supposed to move the top.
No, because I have basis stuff there. Yeah, so, and this is change of basis, so I'm good. Yeah. Okay. So the idea is this: if T BB is equal to like 4, 3, 2, 1, what is T CC? Okay, so the idea is the following then. TBB, or let's say TCC, is equal to, all right, you want to put TBB in the middle, all right, and then what happens is you want to change a basis matrix from C to B, all right, and then you mess around in B, and then you go back to C. Right? Does that make sense? So you start off, right? Your matrix that you want to find is a change of is a transformation from the C basis to the C basis, right? So you got to do the change of basis, starting at the C basis, and then you do your change of basis in B, and then you go back to C, right? And these are equivalent things. So this is where like SDS inverse actually comes from. Okay, and in this example, so TCC is equal to, all right, PBC is, we have this up there, right? It's that guy, 0, 1, 1, 0, right? And then TBB is 4, 3, 2, 1. What is P from C to B? It's this guy inverted, right? Which is apparently also 0, 1, 0, 0, 1, 1, 0? Okay. Yeah, so it's 0, 1, 1, 0 inverse, but this happens to be 0, 1, 1, 0. Okay, so I'm just going to write it out again. All right, and then you do this matrix multiplication, and what do you get? I don't know, because I didn't do it in my prep work, but this isn't too bad, right? So what is this? 2, 1, 2, or 4, 3 times 0, 1, 1, 0. And so that's 1, 2, 3, 4. All right. Any questions? All right. Let's see. 416. Let's continue. 4.8 is call space. And it's like row space and call space, but we don't really care. I'm just going to refer you to the definition sheet here. And the same thing with 4.9 with rank nullity. I'll refer you to the definition sheet. Okay. So we're done with chapter 4. That's like the basis. You can think of chapter 4 as like the basis or like the foundation for like everything we do in this class, right? Because everything is going to be a linear transformation or it has something to do with vector spaces. So do we have any questions, like outstanding like questions about chapter 4 still? Anyone? Yeah.
On the true and false, there's like things about like image and like union and like disjoint stuff. Like,
Yeah.
What do you think about that?
So we can talk about that, right? It was like
You need to know it over the final.
it could show up.
Never heard him say that word.
Yeah, union and it was like union and then like the cap, right? Yeah. I talked about range and like image and stuff, and kernel. But yeah, so for those questions, Yeah, so all those are on the exam, right? Because we know what all those, like if you've heard of it, like kernel of a map is literally like a kernel of a matrix, right? It's the same thing. That's why they're both called kernels. So it's because like all linear transformations can be written as matrices, so then everything in the kernel is going to be, in the matrix is a kernel of the transformation as well. So stuff like that. And the union, I think it's like kind of expected that you know what that is. But I wouldn't like stress too heavily over it. Okay, chapter 6.
Oh yeah, that's really
All right, linear transformations. This is like a chapter that I think at the time is like really confusing for a lot of people. But I think if we talk about it again, and in one semester we actually went back to linear transformations at the end of class, I think it makes a little more sense after we've let it sit for a little bit. So, right, what is a linear transformation? It's a map from T to W, okay, where V has a basis, right? A basis for V, and we call it the B basis, and it's going to be like B1, B2 through Bn, and then the basis for W is going to be the C basis, which is C1 through C2 through Cm, right? And so here, W is going to be M dimensional, and V is going to be N dimensional. And so T from B to C, right? This is the matrix of transformation. Is going to be an M by N matrix. Okay? It doesn't have to be square. It's just that we deal with a lot of square matrices because then we can talk about eigenvalues and stuff like that.
The change of basis matrix.
Is not a linear. Well,
Does that also have to be square?
change of basis matrix has to be square, right? Because if you think about what change of basis matrix is doing, it's a basis for the same vector space. So it's the same dimension. And I think if you look at the definition sheet, I have like in like very like a different color or something, I say change of basis matrix has to be square. So, yeah. Yeah. Okay. Let's see. So there's so you want to show, right? To show that T is a linear transformation, there's a few things. First, you want to show that, all right? So you want to show closed under addition, which is the following. Take like two vectors of V, V1 and V2 inside V, and then you want to show that TV1 plus V2 is equal to TV1 plus TV2. Okay, and then closed under scalar mult is you take K and R and V, and then you want to show that T of KV is equal to K of T times V. Okay? So I'm going to do, I think we'll do like a quick example of this, but in a different context. So these are really similar to doing like vector space stuff, right? It's kind of, the only thing that's different is that you got to like actually plug it into the map, but otherwise it's like kind of similar. And again, we'll see an example in a little bit. Okay, so I think the big confusion, or I guess before we get to that, right? So there's an example, there's a problem on like last semester's midterm or last semester's final where you can abuse linear transformations into finding the matrix of a transformation, right? So if you looked at last semester's final, it was like the one where you had like t of 1, 1, 1 is equal to something, t of 1, 0, 1 is equal to something, and the t of like 1, 1, 0, right? And then you can just take combinations. So that's why they're important. The other, I think, more confusing part is when you have to find the matrix of transformation just given some kind of math and between different bases. So let's talk about that now. So matrix of a linear transformation right. So take, for example, t from P to R to P to R. So we take real value polynomials and we plug them into our map and it gets us another real polynomial. So in particular, right, t of a plus bx plus cx squared, right? So I'm defining what happens to a general polynomial inside my vector space. That is equal to a plus b plus x times negative a plus c, all right, plus x squared times negative a minus b plus c, right? So I have some polynomial with that looks like this and has coefficients a, b, c, and then this is the new coefficients on my polynomial. Okay? So now we want to find a basis. Or B basis for P2R. We call it B. And it's equal to 1 plus x, 2 minus x, 3 plus x squared. Okay, so now the problem is to find TBB. Okay, so what is going on? Oh, I should have erased that. Oh, all right, TBB, right? What is this? This is equal to, all right, it's a matrix where the first column is T of B1 written in terms of basis B. Okay? The second column is going to be T of B2 written in terms of basis B. And then the last column, well, there's only 3 columns, so T of B3 written in terms of basis B. Okay, and other, let's not do the other way first. Okay, so what do we need to do, right? What we need to do is we need to find what T of B1 is first. All right, so that means I need to plug the basis vector into the map first, and I'll get some result. And then I want to write it in terms of basis B. Okay, so first I want to find what T of B1 is. Okay, well, that's T of 1 plus x. All right, and so T of 1 plus x, right? A is 1, B is 1, C is 0. So A plus B is 2. Negative A plus C is negative 1. Negative A minus B plus C is negative 2. So I'll get 2 minus x minus 2x squared. Okay, but when I have have 2 minus x minus 2x squared, right? Notice this is just t of b1, right? What needs to go into this column here? It needs to be t of b1 written in terms of basis b, right? What basis is this guy written in terms of? The standard basis, right? So when I plug this guy into the map, right now the output is in standard basis when I haven't written it in terms of b yet. So this is in terms of standard basis. Right? And now I want to convert this guy into a coordinate in terms of the b basis. But let's not do that quite yet. Right? So now t of b2 is t of 2 minus x. Okay? And so now what is that? You plug in a equals 2 and b equals -1. Right? Into that guy there, and you get 1 plus -2x minus x. So 1 minus 2x minus x squared. Okay? And then this guy here, right? It's just t of b2. It's not t of b2 written in terms of basis b. So this is still in the standard basis. Right? And then if we do the last guy, t of b3, that's equal to t of 3 plus x squared. Okay? And so now a is 3, b is 1, c is 1, and you'll get 4 minus 2x minus 3x squared. Okay. Does everyone follow what's going on up here so far? Right? So I literally just plug all my basis elements into the map. Okay. What needs to happen next? Well, I need to write these in terms of the b basis, right? But that's pretty hard to do. Because the b basis is like not really nice, and you can't immediately eyeball like what the linear combination is going to be, right? So what we can do is temporarily put these guys into a matrix, right? And what is that matrix? Well, that matrix is plugging in the b basis and outputting in which basis? The standard basis. Okay? So now I'll write TBE, right, where I inputted my b basis, but my outputs are just these guys in the standard basis. Okay? So what is that going to look like? Well, the first column is going to be t of b1, which is just 2 minus 1 and minus 2. Okay? The second column is going to be t of b2, which is 1 minus 2 minus 1. And then the third column is going to be t of b3, which is 4 minus 2 minus 3. Okay? And now what? Now we're going to leverage the fact that we can use a change of basis matrix to get us to basis b. All right? So this guy up here, TBB, is really equal to a change of basis matrix from the standard basis to b times t from b to e, which is what we found here in the intermediate step. Okay? So now what's the next step? The next step is actually to find change of basis matrix from e to b. Right? So now we need to find t from e to b. Okay? And so what can we do? Well, here we can vectorize, right? We can vectorize both bases. And so what I'm going to do is I'm going to create the augmented matrix. What goes on the right-hand side? Standard basis, which is?
1 anchor.
Right, but what happens when you have a standard basis on the right, like on the side of the of these kind of things? It's the identity. Yeah, it's the identity, right? So the right-hand side, since it's the standard basis, is going to be the identity. Okay? And so this is going to be 1, 1, 1. And then on the left-hand side, I put my b basis in. Right? This is really p from e to b. Maybe that'll make it a little easier to see. I think this is going to be the notation on the exam, so I don't think you're going to have to like worry about like, oh no, do I go from top down or bottom up? All right, so now we put my b basis in. Well, once my b basis, here's my b basis right here. So that's going to be like 1, 1, 0, 2, negative 1, 0, and 3, 1, 1. Okay? So 1, 1, 0, 2, negative 1, 0, 3, 1, 1. All right, and what do I have to do? I have to reduce until the left-hand side is the identity matrix, and the right-hand side gives me the change of basis matrix, right? In this case, we're actually just finding an inverse. Do we see why? Yeah, right. Right-hand side's identity. So in this case, you'll get 1, 1, 1 on the left-hand side. There's some math. I didn't do it. And then the right-hand side is going to be, because it turns out pretty bad, 1/3, 2/3, negative 5/3, 1/3, negative 1/3, 2/3. And then the last row is 0, 0, 1. Okay? And so now we can find TBB by multiplying these two matrices together. 1/3, 2/3, negative 5/3, 1/3, negative 1/3, negative 2/3, 0, 0, 1. Okay? And then, so this is P from E to B. And then we want to take T from B to E, which is 2, 1, 4, negative 1, negative 2, negative 2, negative 2, negative 1, negative 3. Multiply them together, and you'll get something that is also not very nice. 10/3, 2/3, 5, 2/3, 5/3, 4. Oh, it's 7/3. And then negative 2, negative 1, negative 3. So this is our answer. Yeah.
We just wrote the basis on the left and TB on the right.
Can you row reduce with the base?
Instead of the multiplication, we just like you put the basis on the left and put the TB on the right. That's like,
I think so. Yeah. Yeah, it's the same thing.
you just don't want to.
Yeah. Yeah, I'm pretty sure. Yeah, you can, but I think this way is a little. I think this way is a little more clear of like why we can just take these change of basis matrices. I mean, there are many shortcuts. So the reason why I do it this way though is the following. So in general. In general, right, what are we going to get? We're going to get T from B to C, right? So in this case, it just happened that C up here was also B, but C can be any other basis, right? And so that's going to be P from E to C times T from B to E. Right? Does everyone follow this part here? Okay? So T from B to E is pretty simple to find. You take all your B vectors, throw them in the map, you'll get outputs, and then you throw them in a matrix. Right? So now, here's the idea. So in general, you can do this. The big idea is the following. If the output vector space has the standard basis, then no change of basis is needed. All right? This happens a lot. All right? A lot of times they'll be find TBC, but C, which is your output vector space, right? If the output vector space has a standard basis. So in other words, if C is E, right? What happens? Well, okay. If the output vector space has a standard basis, then C is equal to E, then TBC is really P from E to E, right? Well, okay, T from B to C is really T from B to E. Right? I literally just replace C with E. And then this guy becomes P from E to E, which is a change of basis from a basis itself, which is the identity transformation. So this would just be the identity matrix, which is why you're just left with then TBC is equal to TBE, or in other words, plug your vectors in, get the output, and you're done. Okay, so that happens a lot of the time. This right here, this up here is kind of like a worst case scenario, right? So the big thing about matrix of transformations is look at the basis for the output vector space. Okay? If the basis for the output vector space is really bad, it's a rough problem, you might want to think about moving ahead and coming back to it. All right? If the output vector space has a standard basis, then it's actually not that bad. You just need to grind through and plug in all your basis vectors through it. Okay? So that's that. So these kinds of problems shouldn't be like that spooky. I know that like at the time they're like super confusing, but hopefully if you understand, look at the output vector space basis, that will tell you how difficult the problem is going to be. Okay? Okay, and yeah, in general, right, this TBC is like T of B1 written in terms of basis C, T of B2 written in terms of basis C, etc. Right, T of, I think, what do I have here? T of Bn written in terms of basis C, right? And you should have n columns because your matrix is m by n. Okay. Okay, let's do a special example. So I'm going to disclaimer this example because I don't know. So hopefully McGrath didn't put this on exam, but we were talking about a problem and he was like, oh, I wanted to put this on exam, but I didn't. And I was like, wow, that's a really good problem. I should use it for a review session. So I really hope it's not on the exam. So let's see. So I've like seen the exam, so I don't think it's on the exam. Because I saw the exam and then afterwards he was like, I was gonna put something like this on the exam. And then it's not on there. Because he thought it wasn't like, he thought the computations were too simple, but I thought it was like a cool problem. Okay. So here's the kind of, here's the problem. All right, T goes from M2R to M2R, and the idea is that T of A is equal to A plus A transpose. And so this isn't like, on the surface level, like this isn't like the hardest problem in the world. The first part would be to show that this is a linear transformation. Okay, so part one is to show that it's a linear transformation. Okay, so under plus, right, we take two general vectors in the input vector space, A and B inside the input, which is M2R. Okay, and we want to show, all right, what is T of A plus B? Well, you have A, you plug in A plus B, and you plug in A plus B, you take the transpose of that guy. Okay? Transpose distributes under addition. Under multiplication, it's kind of weird, right? It's like AB transpose is B transpose A transpose. But under addition, it just comes down. So this is A plus B plus A transpose plus B transpose. And then pretty clearly this is equal to A plus A transpose plus B plus B transpose. So you have T of A plus T of B. Okay, so that's good. All right, what about scalar mult? Okay, so now we have T of Ka, which is equal to Ka plus Ka transpose. All right, so that's Ka plus Ka transpose without the parentheses everywhere, and then factor out the K and you're done. So this is equal to K of Ta. All right, so here's where the problem gets interesting. What are the eigenvalues and eigenvectors of T? Right, so T can be represented by a matrix. All right, since it's going from the same vector space to itself, it's going to be the same. It's going to be a square matrix, right? And so when you have a square matrix, you can talk about eigenvalues and eigenvectors. So yeah, so there are a few ways you can do it, right? You could compute the matrix T and then find the eigenvalues, eigenvectors. But do you remember like the reflection kind of problem, where it's like you could just find the eigenvalues, eigenvectors by thinking really hard about like what a reflection was? Remember that? It was on like the recitation homework, right? So this is like this is akin to that. All right, this is very similar. If we think hard enough, we can actually figure out what the eigenvalues and eigenvectors are just by looking at what the transformation is. So, right. So what are the eigenvalues and eigenvectors? Right. So I mean, look, you can go and calculate this. You plug in each matrix, each like standard basis matrix into that map, right? You'll get a 4x4 matrix, and you can take a 4x4 determinant, right, to find a characteristic polynomial. Hope you don't mess up there, and then you can go find the eigenvectors, right? So it's doable. Like that's a perfectly valid way of doing it. But again, it's the same thing with like the reflection map. Well, I guess the reflection map is even more abstract than this one. But like, what are the eigenvalues and eigenvectors? So essentially, what do we want to do, right? So, okay, so T is 4x4, since the dimension of M4R or M2R is 4. All right, okay, so that much is clear. We know it's a 4x4 matrix. So that means, assuming it's diagonalizable, how many eigenvalues and how many eigenvectors should we get? 4, right? So, pray it's diagonalizable. All right, we should have 4 eigenvalues and 4 eigenvectors. All right, and so here's the good news. It is diagonalizable, so that's actually fine. Okay, so now, right, what are eigenvalues and eigenvectors? Essentially, we want to think about when is T of A equal to lambda times A? Someone says symmetric matrices. All right, symmetric matrices. What happens when we plug in a symmetric matrix into this map? Exactly. T of A is equal to A plus A transpose, but a symmetric matrix means that A is equal to A transpose. right? So now this is 2a. So guess what? If we find a basis for the symmetric matrices, what's the eigenvalue associated with that? 2. All right? Does anyone know off the top of their head what the dimension of 2 by 2 symmetric matrices should be? 3. Yeah. Okay. So, all right. So symmetric matrices, right? We get TA is equal to 2a. So for symmetric matrices, we got lambda equals 2. All right. So now we want to find a basis of some symmetric matrices. Okay. So what are they? Well, what's a basis for the symmetric matrix? Anyone?
1, 0, 0.
Yeah?
0.
Okay.
0, 0, 0.
Yeah, exactly. All right, so here's 3 eigenvectors. All right, so lambda equals 2, 2, 2. All right, but I said there were 4 eigenvalues and 4 eigenvectors. We're missing one. 0? No, if it's a linear transformation, 0 is like 0 counts as 0 dimensional. Skew symmetric. All right, what happens when we plug in skew symmetric matrices? You get 0. All right, so skew symmetric matrices. So I think before we move on, it might be wise to like write these in like vector form to like unravel them. So I'm just going to do that. So we're going to have 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1. Okay, so those are our eigenvectors. And then, so now we got skew symmetric matrices. Right? So in this case, T of A is equal to A plus AT. But for skew symmetric matrices, A transpose, or A is equal to negative A transpose. Okay? So T of A is equal to A plus, or A minus A. Right? Because negative A would be A transpose. So now this is A minus A, so T of A is equal to 0 for skew symmetric matrices. All right, so what's the eigenvalue associated with the skew symmetric matrices? 0. All right, so lambda equals 0. And what's a basis for the skew symmetric matrices? Yeah. 0, 1, negative 1, 0. Right? Or I think we're writing them as vectors now, so this is also like, yeah, 0, 1, negative 1, 0 as a vector. Okay? All right, so now we find the eigenvalues and eigenvectors, and there's like a bunch of other cool things we can talk about. So we can talk about what's the kernel of the map. All skew symmetric matrices, right? Because if we plug in any skew symmetric matrix into the map, we get 0. Right? So the kernel is all skew symmetric matrices. Then we can talk about what's the rank of T? What's the rank of the transformation of T? It's 3, right? Because we know one of the eigenvalues is 0, right? And here's the vector in the kernel. So then, right, there's the eigenvalue for T. Okay, and then what else? I think on here, I was like, all right, so you know what this is, and then I have like find TCC, where C equals basis, or C is your eigenbasis. Does anyone know what this is? Off the top of their head?
Just the diagonal.
It's the diagonal matrix associated with this guy. Okay, right, so TCC with respect to the eigenbasis is 2, 2, 2, 0. Okay, and then what is TEE? So we're kind of working backwards, right? Which is the transformation, I guess the transformation up there that we want. Well, that's equal to P from C to E, TCC, P from E to C, right? And what is this? Well, we know TCC is a diagonal matrix. So what if we call this guy S, and we call this guy S inverse? Right? And what is S? Well, S is going to be the eigenbasis, right? So S is, so your eigenbasis, you have your three vectors there, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, and then you got your straggler for lambda equals 0 over here on the left-hand side. So it's 0, 1, negative 1, 0. And then D is going to be 2, 2, 2, 0. And then you have S inverse, which we're too lazy to calculate. But that's how you do it, yeah.
Is the number of eigenvalues always equal to the matrix?
Eigenvalues is the rank of the matrix. No. Right? If you have a Jordan block for 0.
Like, oh no, I don't like non-zero eigenvalues.
Is that true? No, because if you have Jordan block for 0, that also messes with the number of eigenvalues. Yeah. So just defective matrices like screw up a lot of things. Okay. Let's see what's next. Okay. I think let's take a break for now, and then we'll come back and in like 10, 15 minutes, and then we'll do some ODE stuff. Yeah. I know that T of A is equal to 2A.
Yeah.
So essentially this is like A, like TV is equal to 2V.
TV is equal to 2V.
Right?
Okay.
Yeah, because A is like my input, right? And then 2 is like just the eigenvalue associated with that.
Oh, okay.
Yeah.
Okay.
How are you able to say that TCC is just diagonal?
The diagonal matrix? So whenever you have something with respect to the eigenbasis, it's either going to be a diagonal matrix or the Jordan matrix associated with it. That's what I always do. Just because you can do this, right? So if you look, this is A is equal to SDS inverse. This is what TCC is. Like if TCC is the diagonal matrix, when C is the eigenbasis. Oh, C the eigenbasis.
How'd you get a group?
I got it like last week.
But the registrar has it booked from like the very beginning of the semester.
Get fucked.
I heard this test we put in 7. What does that mean?
I mean, stuff like this. Stuff like this. I mean, this is a problem he was going to write for the exam, right?
This is like, oh god, that's terrible.
Yeah.
So
So, I mean, just focus on basics. I would say just.
So like, I know how to do all Jordan, like
Yeah.
all like that stuff. Like, so she knows stuff like lambda, like all that like lambda stuff, AB equals lambda B. And, like,
Yeah. I mean, that's like a standard definition that you should know. Yeah.
I just haven't used that for so long. Just 'cause I know, like,
For this, do they ask you to find TCC?
I literally made this up myself.
Okay, so you're just like kind of thinking about.
He only told me about the map, and then I just went with there from it. Yeah.
So they're saying find the matrix, the matrix of linear transformation.
With respect to the eigenvalues.
So you're plugged like. So that's why you're plugging in. S is the eigenbasis.
Exactly. S is the transformation from the eigenbasis back to the standard basis, but that's always just the eigenvector. right? Because if you think about it, right? 1, 1, 1, 1, right? If this is like the E basis, right? And then you put the eigenbasis in here, right? Well, that's just the eigenvector. Well, you don't really do anything, right? Because you want the eigenvalue. So then this is C to E, right? Because that's literally what this is. And then S inverse is just you invert this guy.
For this,
Yeah.
is the reason why symmetric matrix is because you just want to get A plus AT into that form where it's like an eigenvalue. It's
Yeah,
like
exactly.
So that's why you just use that property.
Yeah, so you kind of had to just like guess that it was a symmetric matrix.
So you're just kind of forcing it and just
Yeah, so
happens.
it's like an educated guess there. Yeah. There's really not other like. I mean, the other way of like grinding it out and working backwards to get all this is fine.
Fine.
Yeah, it's just. I don't know. I think it's a little more work because I think if you just left the problem like this for your answer, or if we like structure the problem, like if we ask for this problem before asking for what the matrix was, then it's gonna be like a little more like it's gonna be a little more weird, I guess, if you like solve for the matrix and then went backwards.
Yeah. And also for TE, is there a reason why A happens to be this?
It doesn't have to be TE. It's literally. Actually, no, it has to be TE because the this eigenbase, this eigen, what we're just talking about here, when you write the eigenvectors out as a change of basis matrix, you have to be going to E.
And
right, because you want to row reduce this guy, so you get the identity matrix on the left.
Yeah.
Right, and then the right hand side is the change of basis matrix from C to whatever basis. But if it's E, then you already have the identity matrix.
Yeah.
So then you're done.
So then, because if TE just happens to be A though.
Yeah, it is.
It's
So this is the matrix of transformation for this guy. Because, I guess I didn't specify basis by what I should have specified the standard basis. Yeah. If the basis is ever unspecified, just write, like, assume standard basis and move on. Yeah. Guess 5 vectors and then plug it in perfect. You should get the same answer though. Yeah, like A times that guy plus B times that guy, C times that guy is equal to that. Yeah, and then you do A times the right hand side, B times 2x squared, C times x squared. Yeah, you should get the exact same answer. Yeah, a lot of people have done that actually. So just, yeah. So just keep on. I mean, I think Navy sent out some solutions as well, right? Oh, really? Okay, yeah. No, you should get my answer. So just see if you're solving for something wrong or if there's some mistake. Yeah. I assumed it was. I assumed n was 2 though. Yeah, you plugged in 0. Yeah. But you did not take the derivative. No, you know, because R is a vector. Right? We're talking about vector, not. So for vector functions, you don't do the derivative. You just plug in that vector. Yeah. So there's a difference between functions. So it's true, and that's because you can make a linear combination to get to the basis that's 1, 0, 0, 1. And then you know where the basis vectors get set. And then because the basis vectors get set somewhere, you can't have the bases get set to different places. So you can't have like 1, 0, like you can't have T of 1, 0 So you're transforming one base into another. T of 1, 0 is going somewhere, and T of 0, 1 is going somewhere. Right? But that alone will define the entire thing.
So we're going to do that using R2, so we can define this.
Exactly.
I would be too.
everything all around, really, I think
Oh, there's first goal.
I figured something with like the RNS would be imaginary example.
I think honestly, if you can get the correct direction it's going, so that's where you use the matrix x, you know, x prime is equal to ax. So if you plug in like x is equal to 1, 0, it'll tell you what the tangent vector is.
Watching the most disturbing prank ever.
They kind of come around, and then all these people go and get blindfolded, and then they're gonna make out with someone.
It was messed up. What very messed up.
Yeah, go for it.
So in this question, it requires that you would change from CE and then E to B.
Okay.
And you can't just throw them into matrix and do like C. Can you?
Oh yeah, you can. Yeah, that's literally what you do. Yeah.
It's like, okay, so it's exactly the same thing as doing just.
Yeah, it is. It should be.
Okay, I thought I just made a computational error.
Probably, yeah. No, but that's the long way. That's definitely the long way. Just put C and B, and if you had already had B to C, just take the inverse of that matrix. Right. Yeah.
Oh, yeah, it's well. Hey, was that what's on the floor?
It's not like this white
It's like
ball.
sprinkles. Get out of the screen. Did you like it? What are you looking at for? Also, the screen light doesn't block your phone that much.
Most disturbing prank of all time.
After this, I'm going straight to hell.
Yeah, so that's why like when I went to court,
So it was a thing,
yeah,
but then they
they couldn't really do it because of something. I don't know.
It's so looking pretty bad. Yeah.
That would be really bad. Well, Ken is a force He comes in patterns. I love it. I'm not gonna lie. It's super fun. It gives you basically out-of-body experiences in like 30 minutes. You're just chilling. It's super non-committal. I'm just saying. From like from a degenerate perspective, hear me out. From a degenerate perspective, it's very mild. Like literally just like you can't feel your arms and legs and you try walking and you just can't. That's like the end of the work. It's like sleep paralysis but like not natural.
What associate that with anything I wanted to have to I'd be like, I don't know what he's talking about. Just go to sleep.
You're not going to say
Yeah, the Twitch stream's still going. Hopefully.
What?
Confessions live.
No. They know I'm trying.
Okay, so I'm gonna switch to here soon. So let's continue. Yeah. So I think I'm just restricted to this board now. And the reason is because I want to use these screens in a little bit, so we need to move this stuff now. So I think so on like Calvin's midterm, there was like one question where it was like find a basis for like the column space, and I like essentially abused the fact that the span of eigenvectors associated with non-zero eigenvalue is the column space for a diagonalizable matrix. I have a proof here that we're not going to cover for the sake of time, I think. It's pretty long. So if you want to read it, you can go ahead. It's under the prep notes for this section. So I think let's talk about the Lichtenfeld's midterm problem, where I essentially made a pretty big assumption that turns out to be true, but we haven't learned essentially we haven't justified why the assumption I made was true. So let's talk about maybe a proper way to do this problem instead. So Lichtenfeld's midterm problem is the following, right? We have an A as a 5x5 matrix. Lambda equals 3 is the only eigenvalue. And you know that the geometric multiplicity of lambda equals 3 is 2. And you know that the dimension of the kernel of A minus 3i squared is 4. Okay? So now you want to figure out how many blocks there are. Determine like what the Jordan blocks are. So here's what we have, right? The geometric multiplicity equals -3. Lambda equals -3 is 2. So I think I actually need to switch over now because I don't have this prepped out. Okay. So what are the Jordan blocks, right? So what we want to do is that we want to write it in this way here, where this is equal to the geometric multiplicity of lambda equals 3, right? That's the definition. The dimension of the kernel of A minus 3i equals 2 is the definition of the geometric multiplicity for lambda equals 3. Let's make this thinner. Let me make that thinner. Okay, so, all right, so how do we know what are the Jordan blocks? Well, dim cur equals 2 also tells us the number of Jordan blocks, right? Which is 2. So my cycles so I have a 3 cycle and a 2 cycle, or a 4 and a 1 cycle. All right, so I either have a 3x3 block and a 2x2 block, or I have a 4x4 block and a 1x1 block. Okay? So I think, so the way I justified it on, I think, the canvas thing was I said, hey, dimension of, I said dim of cur of a minus 3i cubed was equal to 5, right? I said that this is the zero matrix. This is true, but we don't have the tools to prove it. We can't just state this. Okay, so what's another way to do this problem? All right, so we're going to write out again. Dim cur a minus 3i is equal to 2. Dim cur a minus 3i squared is equal to 4. All right, assume that we had a 3 cycle and a 2 cycle. So I guess I need to pull down the big screen. Let's do that. Okay, so now what? Okay, so I know that if I had a 3 cycle and a 2 cycle, the dimension of the kernel of, okay, so this implies there's a 3 cycle. Okay, so assume then we have a 4 cycle and a 1 cycle. What does that mean? That means that the dimension of the kernel of a minus 3i cubed cannot be 5. So what does it have to be? It has to be 4, right? So the rank can't, so the nullity can't go up, right? That doesn't make sense. So the nullity can only keep on going. Okay, so the nullity can't go down. It can only keep on going up, right? So if it's not 5, then it has to be 4. All right? Okay. So what does that mean? Well, that means that, okay, let's say I had a 4 cycle. All right? So let's say that, let's see. Assume that there is a 4 cycle and 1 cycle. Yeah. Okay. So assume that we have a 4 cycle, right? Okay, so I already said that. So if we assume that there's a 4 cycle, this means a minus lambda I to the 4th times v g is equal to 0, right? But a minus 3i cubed vg is not equal to 0. A minus 3i squared vg is not equal to 0. A minus 3i vg is not equal to 0. Right? This is what it means for there to be a 4 cycle, right? The 4 cycle has to satisfy all of these conditions at once. Okay, what's the problem here?
A minus 3i cubed and a minus 3i4 basically have the same kernel, so you cannot have single vector satisfy.
Yeah. So I'm looking at cube squared and cube, right? You were looking at cube and a 4, but it's the same thing, right? So the dimension of the kernel of a minus 3i cubed is 4. The dimension of a minus 3i squared is equal to 4 as well, right? So what does that mean? It means that the column space is 1, right? Or the rank of the matrix of a minus, so this means the rank of a minus 3i squared is equal to 1, and this means that rank of a minus 3i cubed is equal to 1. That's also equal to the dimension of the column space. Right, so these all mean the same thing. Dimension of the kernel of a minus 3i squared equals 4 means that rank is equal to 1, means that the column space of a minus 3i squared is equal to 1. Okay, so the problem comes here. Right, the dimension of the column space of these two matrices are 1. So what does that necessarily mean when I plug in VG and it's not equal to 0?
It has to be 0 if the first one is 0. Because they have to, all of them essentially have the same column space and the code. So.
Not quite.
Because like if the dimension of the kernel for a minus
Yeah, so that's true, right? If this were 4, then a minus 3i cubed would also be, like these guys would all be the same matrix.
Yeah.
Yeah, that's true.
Yeah.
So I think the way you want to think about it is, if this is satisfied, then these can't be satisfied. All right? Or another way you can think about it is, if this term is satisfied, if a minus 3i cubed VG is not equal to 0, this vector is the same vector. These two in pink are linearly dependent because their column spaces are both 1. All right? And they have the same like matrix that you're squaring over and over again. Okay? So the idea is that if you had a 4 cycle, it's impossible to get linearly independent eigenvectors or linearly independent generalized eigenvectors here. All right? So these would not be linearly independent. Because of this up here. Yeah.
Also, we show that if like if a squared is 0,
Yes.
then the kernel of a squared has to be a superset of the kernel.
Exactly.
Right?
Exactly. That's
So
another
if
way.
A minus 3i squared, the kernel of a minus 3i4 will contain every element which is
Yeah. So the kernel of this guy, the kernel of a minus 3i to the 4th contains every vector in a minus 3i cubed. Right? And since they're the same kernel size, or they would be, or actually let's just look at these two. Right? A minus 3i cubed contains all those kernel vectors in a minus 3i squared. Okay? So if I pick something not in the kernel of this guy, it's not going to be in the kernel of this guy. And then you know that they have to be linearly dependent on each other. So that's one way. I think that's the way he wanted you to do it, because the other way, you would do it, you have to invoke some theorem that we haven't learned. But do we want to explain this? Do you want me to explain this again? Just again? So, okay. Again, what's happening is, assume, right, we know that we have either a 3 cycle and a 2 cycle, or a 4 cycle and a 1 cycle, right? So assume that we have a 4 cycle and a 1 cycle. What do I need to do? I need to take all of these powers, right, to get a 4 cycle, okay? The problem is, all the vectors in the kernel here are inside the vectors in the kernel up here. Right? And then these vectors are inside the kernel of that matrix. But the problem is the kernel stops growing. Right? The kernel stops at 4, which means that all the vectors in the kernel of a minus 3i squared are the same vectors in the kernel of a minus 3i cubed. All right, so these two share the same kernel. What does that mean? It means that if this is non-zero, then you're going to get the same output. Vector, right? A minus 3i cubed times VG is going to be a linear. It's going to be a linear multiple of a minus 3i squared times VG, because the kernel stops at 4. Okay? Yeah.
So what does that tell you once you know that?
So it tells you you can't have a 4 cycle. So then you must have a 3 cycle.
So you should always get the 2 linearly independent vectors for those two if it's gonna.
Yeah, these guys all have to be linearly independent. right? Because where do we end up putting these three vectors? We put them in the S matrix, right? This guy, this guy, this guy, and then VG, we put in the S matrix, right? If these are not linearly independent, then you can't put them in the S matrix because you need to invert the S matrix. Okay, so I think that's it there. And so in Jordan form, just like for Jordan canonical form in general, just like know how to compute it and know how to mess around with like block sizes and dealing with like block sizes. Yeah. Yeah, so if it's 5, right, then A minus 3I cubed is a 0 matrix, which means we have to have a 3 cycle. Okay? But we're assuming that we have a 4 cycle. So this guy can't be 5, right? So in particular, if it doesn't grow, it has to stay the same, and so it's still 4. Okay. Yeah.
Did you say that for, like, at least for most Jordan canonical form, that like the column space should like decrease every single time, and like the rank should decrease every single
No, so it will get, so the idea, so this is true in general. I think I've written this down somewhere, but essentially, so in general, rank A to the K is going to be greater than or equal to rank of A to the K plus 1, right? So this is rank we're talking about, not nullity, right? But the idea is if rank of A to the K is equal to rank A to the K plus 1, then rank A to the K is going to be equal to rank A to the like M for every M bigger than or equal to K. So the idea is if you get stuck, right, if the rank stays the same, it's always going to stay the same. It's never going to randomly drop down again. So which is why I knew up there that if the dimension, like the dimension of the kernel can't like decrease, it can only keep increasing or stay the same. Yeah. But this is a really special problem just because like the only reason why this problem worked out is because the dimension of the kernel was 4. Like that's actually like the only reason why it works out. I think there's going to be like you'll probably have like more hands-on type of problems where you can actually like mess with the matrix and figure out like the cycles rather than just sitting here and like playing with it abstractly. Yeah. Okay. I think that's it there. Okay. So this is an interesting like that's probably useful for true false as well. Dealing with true false problems when you have like powers. So let's talk about eigenvalues and eigenvectors real quick. And diagonalizability. So I think mostly I want to refer you to the definition sheet. There's just a few highlights. The first is know how to use and recognize. My computer's freezing. AV is equal to lambda V. That's like by far the most important like eigenvalue, eigenvector definition you're going to get. So if you looked at last semester's midterm, or last semester's final, there's like the one problem where they give you AV equals lambda V, but except with like actual matrices multiplying stuff out, right? So you need to be able just to like recognize when you're given this. Additionally, like know the relationship between the linear transformations and like diagonalization or Jordan canonical form. Right? It's kind of what we just did on this board behind now, but you can't see it. where the eigenvalue the eigenvector basis is essentially a change of basis from the standard basis, or from the eigenvectors, or from the matrix of eigenvectors is a change of basis matrix from the eigenvectors back to the standard basis. So stuff like that. Also, if you see matrix powers, that means diagonalize or Jordan form, right? You're never going to be taking matrix powers of like don't iterate through a matrix power. Like if you see a matrix power, you can do this with it. I think, what else off the top of my head? I think, yeah, just refer to the definition sheet. I think most of it is there. And oh yeah, maybe recognize, like, I think in the recitation video, I did something along the lines of like recognizing when you have like different size blocks. So like recognizing different size Jordan blocks. And then I'll refer you to the definition sheet. Okay. Any questions there? All right. Yeah. So I think the most common Jordan block to the power is going to be like 1, 1, 0, 1 to the n. And if you actually just work out a few of these guys, it's 1, n, 0, 1. Yeah, just like do it. I mean, there'll always be a pattern with these Jordan blocks. So do a few and then see if you can find a pattern. And then like don't actually multiply out. I think on last semester's final it was like 2 to the 2018. Like don't calculate that. I mean you can't. So just leave it as is. Okay. Let's see. ODEs I'm gonna skip. We kind of had a midterm just on this recently. So okay, so I think the one thing was like no variation. Like he was like, there's no variation of parameters on the exam. So technically you can use variation of parameters. Just don't be a dingus and use it when like x squared is in front of your like y double prime term. Like just know how to use it. Again, reduction of order is going to be safe throughout, and just I would highly recommend using that instead. So ODEs, I think, I mean, just grind out ODEs. There's really nothing to do here. Okay. So systems. Okay, so in systems, I want to talk about a few things. Okay, 1 second. Okay, so yeah, so for systems, I'm going to jump to 9, 9, and 9, 10, so which are phase portraits. So I think it's pretty clear that these will probably be on the exam, mainly because it's like the one thing that wasn't covered before the last exam. So like, oh really? Yeah, I mean, this is either on the exam or not on the exam. I mean, it makes sense that it would be on the exam because like we covered it and it was after our last midterm, right? So, let's see. Well, let me. No, I'm trying to pull up a problem on here. 1 sec.
Oh my God. I just saw it on the syllabus and I moved what it is. LOL. I've asked you their classes.
Okay. Yeah, so let's do the following. Let's have x prime equals 0, 2, negative 2, 0. Right? All right, so x prime is equal to 0, 2, negative 0, x. And so we want to find the face plane portrait and draw it. So here, what do we want to do? We can do the following. So you find the eigenvalues and eigenvectors. So det A minus lambda I, which, by the way, please don't calculate this incorrectly on the exam. And so you'll get this. All right, and then that's going to be lambda squared plus 4. So lambda is equal to plus or minus 2i. Okay, and so instead of like blindly memorizing like what the heck's going on like in that table, like actually like write out what the solution is going to be. Right, so the solution here is going to be like c1 cosine 2t plus c2 sine 2t. Right, so this is what your solution is going to be. Okay, but notice what happens when t increases. You just kind of just spin around, right? So, oh wait, this is definitely, is that? No, this is that the okay? No. So there's a system that I didn't do. Yeah. So what are the eigenvectors? I mean the eigenvectors. So here you got like negative 2i, 2. So this is lambda equals 2i, right? 2i, negative 2. Negative 2 minus 2i. So you can let v equal 1 and then I. Okay, and then here, let's see. So you got, c1. Well, you got cosine t plus, or cosine 2t plus I sine 2t times 1, 0 plus I times 0, 1. All right, so now this is x of t. And then so this is equal to cosine 2t, 1, 0, plus I cosine 2t, 0, 1, plus I sine 2t, 1, 0, minus sine 2t, 0, 1. Okay, and then so that's going to be, you want to group the reals and the imaginaries. And that's going to be c1 times cosine 2t, 1, 0, minus sine 2t, 0, 1, and then plus c2 times e to the 0t, and then you got cosine 2t, 0, 1, plus sine 2t, 1, 0.
I would think that should be 0, 1 times the negative sine 2t.
Yeah, you're right.
Is there right to just write cosine 2t, sine 2t in a single vector? Like cosine 2t and then negative sine 2t?
Yeah, you can like combine these. Yeah. That's fine. Okay, and then so now, like if you think about what's going on, there's no e to the at that's like screwing around with you, right? Like e to the at out here would like either blow you up or shrink you in, right? So since there's no e to the at, this just means we're like spiraling around, like we're just circling around the origin. So here, here's what you get, right? You'll just circle around the origin, and you'll have points that look like that. Okay, and now the important thing is you need to figure out what direction these guys are spiraling. Okay, yeah, and so the way we find how to find, the way we get one of these guys is we plug in a vector, right? We know x prime is equal to this matrix times x, right? We have x prime is equal to 0, 2, negative 2, 0, x. So if I plug in some x, I get my tangent vector at that point, right? And so what's an easy x to plug in? Like literally you can just name it, yeah. So you can let x equal 1, 0, right? So that means we're at like this point right here. And then, right, x prime is equal to 0, 2, negative 2, 0 times 1, 0. which is 0, negative 2. And this tells you what direction the tangent vector is going in. It's going in the 0, negative 2 direction. So at this green point, we're going in the 0, negative 2 direction. All right? And so what does that mean? That means we're rotating this way. Yeah, clockwise. All right, so this is like what we expect from these kinds of problems. And so let's see. Yeah.
Are these like ones with imaginary values? Are they considered stable or unstable?
So this, so since it's a linear system, it's a stable center.
Okay.
Yeah. Yeah.
He said it wasn't.
He said it's nothing.
Yeah, you like, so the book's actually technically like wrong here. It's like not like we don't actually know how to characterize these, I think. So they just like generalized it big time.
So if you say center point, you're fine.
Yeah, if you say center, you're gonna be fine. Okay, let's see, what else? Okay.
They should make a video for classification called Schrodinger's cat. What?
Okay, now let's do like x prime is equal to negative 2, 1, negative 1, 2. Okay. And then, so what is this? Det A minus lambda I. Oh, let's see. Hold on, I did something wrong here. There. Zero, 1, negative 1. Oh, 0, 1, 1, negative 2. My bad. Okay, so det A minus lambda I is negative 2 minus lambda, 1, 1, negative 2 minus lambda. Okay, and that's equal to, this actually becomes 2 minus lambda, or 2 plus lambda squared, because you can factor out like a negative 1 and then minus 1. And so that's going to be lambda squared plus 4 lambda plus 3. And so that's lambda minus 3, lambda, or lambda plus 3, lambda plus 1. All right, and then if you think about, right, lambda equals negative 3, you'll get the following, 1, 1, 1, 1. And so the vector is 1, negative 1. And then lambda equals negative 1, you'll get 3, wait, hold on. Negative 1, 1, 1, negative 1, and so the vector is equal to 1, 1. Okay? And then, so now what? So now when you graph it, right, you want to graph your eigenvectors whenever they're real. So here I have 1, 1. And you want to, like, just make sure you, like, throw the lambda with it. Lambda equals negative 1. And then here I got negative 1, 1. That is not going through the origin. Or 1, negative 1. And this is lambda equals negative 3. Okay? And then what's going on is that since these guys are like, so when you have negative eigenvalues, they're pointing towards the origin. Okay? And then from that, you can guess that all your points from out here are just going to fly towards the origin. And which one are they going to fly closer to? I think they're going to fly closer to the negative 3. Because negative 3 is like a stronger eigenvalue. So what's going to happen, yeah, it's more negative, so it's going to go like that. So that's your point, and then it's going to hug negative 3 longer. And then they're all coming in towards the origin. And then here's the same thing.
Very close to negative.
Sorry, if they're what?
They're really close to like the land equals negative.
Yeah. Yeah, they're just going to be like a line if they're closer. Yeah. Okay, and so this is a stable node. So whenever you have everything like either leaving a point or exiting a point, that's going to be a stable node. Or no, if everything's approaching a point, that's a node. Stable means everything's going towards it. Unstable means everything is falling apart. Yeah.
There's one question that was like, do trajectories ever cross?
No, they shouldn't.
But like, even like, if you have like a saddle point, like when like
No, even when you have a saddle point, they shouldn't cross. Yeah. Okay, all right, let's take a look at this problem. So this is a spring 2018 midterm problem. Okay. So if you have dx dt equals x times 1 minus y squared, dy dt is equal to y x plus 1. All right, so now the idea is determine all the critical points and then classify each critical point. Okay. So how do we determine critical points? Yeah, so whenever these guys are 0. Okay? And so we kind of have to case it here. So this is really like x prime, right? And this is really y prime. So we need x prime is equal to 0. Okay? And so when is x prime 0? This is 0 when 1 minus y squared equals 0 or x is equal to 0. Right? You look at x prime, either x is 0 or 1 minus y squared is 0. So what does that mean? This means y is equal to plus or minus 1 or x is equal to 0. Okay? And then now you got to look at the y prime is equal to 0 case. And so what does that mean? That means either y is 0 or x is negative 1. Or, wait, okay, so what can happen? Y can be 0. Yeah. So we got so y is equal to 0. Or x plus 1 is equal to 0. All right, so in this case, x is equal to negative 1. So y is equal to 0 or x is equal to negative 1. So now you have to play around with stuff, right? Because you need both of these to be 0. So if x is negative 1, right, what does y have to be? Yeah, y has to be plus or minus 1 if x is negative 1. Why can't y be 0 if x is negative 1?
The second one doesn't work.
The first one. Right. If x is negative 1, then, right, if x is negative 1 over here, then 1 minus y squared has to be 0. So what do you have? So you have like negative 1 and 1. You have negative 1 and negative 1. All right, so you have those points. Okay, now we say the same thing. What if y is 0 here? X has to be 0. Right? Because if y is 0, on the right-hand side, right, then 1 minus y squared is not 0, which means x has to be 0. So then we know 0, 0 is a critical point. All right, now you just have to keep on playing this game, right? So what if y was equal to positive 1? Oh, so if y were positive 1, then x has to be negative 1. We already have that. If y were negative 1, then x has to be negative 1, so we have that. And then we have the case when x is 0, y has to be 0. So we've mapped, right, so there are 2 values here, 1 value here, 1 value here, 1 value here, and we've mapped them all out. There are critical points. Okay, so those are our equilibrium points. So part B is to classify them. All right, and how do we classify this? So what do we have to do before we plug in our critical points? Yeah, so you have to take the Jacobian matrix. Right, so J of xy is going to be equal to this guy, this thing, let's call it F, and this, call it G. All right, so now this is going to be F derivative x, F derivative y, G derivative x, G derivative y. All right. And this is not a determinate matrix. So in our case, right, what is F derivative x? 1 minus y squared. All right, what is F derivative y? Minus 2xy. All right, what is G derivative x, y? And what is G derivative y? X plus 1. Okay, so now that we have a Jacobian matrix, now we can go calculate at every point if it's a stable node or unstable node, or a saddle or spirals or whatever. So, okay, so we have our 3 equilibrium points. So here's J. Let's do 0, 0 first. Right, so you plug in 0, 0 into this matrix, and you get 1, 0, 0, 1. Okay, what is that? So we need to find lambdas, right? We need to find our eigenvalues. Okay? So eigenvalues are 1 and 1. So now we can classify this point. It is unstable node. Yeah. Okay, J of negative 1, 1. How do you as a node? Is because these have real eigenvectors. Yeah. Okay, so now we do J of, well, what do we have? We have negative 1, 1. Okay, so now we got 1 minus 1 squared, so that's going to be 0. Negative 2 times negative 1 times 1, so it's positive 2. Y, which is 1. And then x plus 1, that's 0. Okay, so now we got this guy, 0, 2, 1, 0. So det A minus lambda I is equal to lambda, or negative lambda, 1, 2, which is equal to lambda squared minus 2. Okay, and then lambda is equal to plus or minus root 2. So what is that? It's a saddle. And now we find J of negative 1 and negative 1. And so now what do we get? We plug in negative 1 in the top left, you get 1 minus 1, that's 0. Plug in negative 1 in the top right. Negative 2 times negative 1, that's 2. Times negative 1, it's negative 2. Okay, y is negative 1. And then negative 1 plus 1 is 0. Okay, and then you find the determinant here. Determinant A minus lambda I was equal to negative lambda, negative 2, negative 1, negative lambda, and that's lambda squared minus 2 still, and so you get the same eigenvalues and and so that's also a saddle. Okay. Any questions about this? I also do another example in my recitation where we do the same thing. So if you look at the recitation video, I'd say it's pretty good. Either one of these or the drawing ones, I think it's fair game. Okay. So one thing is that if you watch the spring, I think if you watch the review session where I did like the spring 2018 exam, right? There's a question where you have to characterize all the equilibrium points of a matrix, all right? Be really careful when you're factoring these characteristic polynomials. I think just in general, just like try to be careful with like these calculations, because if you get like if you get the characteristic polynomial wrong, you're not going to get many points. If you factor something wrong, you're not going to get many points. So just like be careful with the calculations throughout. With diffie-qs, I would just go through and just chug some diffie-qs. Like there's really nothing to do there. And then we solved some matrix diffie-qs up here. So there's really nothing to do there. So okay, I think let's end it here. I think this is a good spot to end. So Nibby has office hours, I think, tonight. And then I'll have office hours tomorrow after I get done with my essay tonight, hopefully. But we should be available pretty much all day tomorrow. So if you have any questions, just like stop by. Yeah, Nibby also is going to pull like an all-nighter. So he'll be around. I will not be pulling an all-nighter. So anyways, thanks for coming. And I'll see you guys. Good luck. See you guys Friday. Yeah. That's fair. That's definitely fair.
Okay, but like, so the method in the book is what we should use, right?
Just SDS inverse or SJS inverse.
Sorry, not a matrix exponential. I mean like e to the AT. Like calculate that.
That is a matrix exponential.
Okay.
E to the AT is the matrix exponential. Okay. So you do S e to the JT S inverse, or S e to the AT S e to the DT S inverse.
Yeah, okay. So that's the method we should use.
Yeah.
Okay, and also
I guess definitely know how to do it for a diagonal matrix and a Jordan matrix.
Okay.
Right, because the Jordan matrix is like you get the t squared over 2 factorial stuff.
Yeah,
right.
It's just going up.
Going up, and then the diagonal one's just literally the diagonal one.
Okay, and also when you say rank of a to the k is greater than or equal to rank of a to the k plus 1.
Yeah.
So basically the rank is decreasing.
Yes.
Until it's equal or 0, right?
Right. Exactly.
Okay, so if it's decreasing, doesn't mean it's decreasing forever.
Exactly. Yep. Right.
Sorry, I like zoned out, but how did you get these? Why are there only 3 equilibrium points? So I got up to like this part, but how do you get from like here to like the 3?
So you have to like consider each case separately. I think there's a review session after me, so let me try to get out. Do you mind meeting me like outside real quick? Yeah.